Hello, this is Daniel, and I'll be presenting about polyparaphenylene terephthalamide. PPPT, or Kevlar. This polymer was invented in the 1970s by an American chemist named Stephanie Kwolek. Originally created as a replacement for the production of racing tires, Kevlar is now available in several grades depending on the required characteristics. Kevlar fibers are defined as a aromatic polyimide, or aramide for short. It consists of long chains of molecules that form strong hydrogen bonds with one another. Kevlar can provide several advantageous characteristics, such as its high tensile strength, rated at about 3,000 megapascals, compared to nylon at only 75 megapascals. Kevlar also has very good heat resistance. Unlike other plastics and polymers, Kevlar does not melt. It can withstand high temperatures up to 450 degrees Celsius or 850 degrees Fahrenheit, and low temperatures down to negative 200 degrees Celsius or negative 320 degrees Fahrenheit. Because of its structure of the fiber chains and interchain bonds, Kevlar also has very good impact resistance that can help to prevent cutting and penetration depending on the number of layers available. Also, because of its relatively low weight, Kevlar can make an excellent substitute for metals or ceramics with similar characteristics that can help to increase the effective workloads of certain processes. The chemical composition of Kevlar is created through a condensation reaction using a combination of amine or paraphenylene diamine and acid chloride or terephthalic acid. The creation of Kevlar fibers, the PPTD solution, is spun using a process called wet spinning. In this process, a winding spool is pulling the polymer solution through several mechanisms to contour and shape the fibers into the desired threads. A container holding the polymer solution is heated until the solution is at its desired viscosity, which is then fed into filter packs, which help to separate any dust or sediment that could interfere in the process. A metering pump assists in the movement of the polymers as it is pulled through a spinneret, which extrudes the polymer solution through several small openings, forming several strings of fibers. These fibers are then pulled into a coagulation bath. Typically, water is used depending on the type of polymer. The bath allows the polymer solution to precipitate and form protofibers, which are then pulled along several rolling pins to be air dried and hardened into filaments. At the end of this process, the spools of fibers are cut or woven and then treated for its intended application. For its high tension and impact strength, comparable to its relatively lightweight, Kevlar can be found in several applications, like in sports equipment, military ballistics protection, and also for aerospace fields. For sports like tennis and badminton, the tensile strength of the string for rackets is crucial. For these applications, Kevlar is packed into a multi-filament string where several filaments of Kevlar are glued and strung together in a similar process mentioned previously. The multi-filament strings are then coated in silicon to protect the string and also to prevent any fraying during play. The advantage of multi-filament strings is that manufacturers can vary the type of filament inside the string in order to achieve the desired effect. In military applications, Kevlar provides a suitable material for the production of bulletproof shielding and apparel for military personnel. For Kevlar vests, large spools of the woven Kevlar fabric are laid out to be cut according to the desired shape and size. Several layers of the same template are cut and stacked together, usually with a minimum of 8 layers, all the way up to 25, depending on the desired protection. A machine is typically utilized to cut several layers at a time using a cutting wire. And once all the cutting is complete, a template is utilized to help guide workers to sew the several layers of Kevlar sheets together. Several straps and shells are also sewn in to finish the look of the vest, where it is then tested and inspected for its overall effectiveness. For aerospace applications, Kevlar can be utilized for both interior and some structural applications. The key factor is in the use of Kevlar honeycomb cores. These honeycomb structures provide considerable structural integrity and fatigue resistance while keeping the structural weight quite low. These structures are created from long rolls of Kevlar sheets, wherein a machine lines adhesives and stacks more sheets of Kevlar together. Once a certain sheet thickness is reached, the machine presses the Kevlar sheets together to ensure that the adhesive uniformly adheres the sheets together. A worker then places several guide rods along the side, which makes open cells in the structure. After being placed in a stabilization oven at 350 degrees Fahrenheit, the structure now resembles the honeycomb geometry. In the next stage, the structure is then dipped into a phenolic resin bath that evenly coats the walls and is then placed in an oven to be cured, then weighed and inspected. Often a cycle of dipping, curing, and weighing is necessary to achieve the desired thickness for the specific applications. Finally, the honeycomb blocks are cut into the honeycomb sheets through the final machining processes. These Kevlar honeycomb structures can be found in the interiors of aircraft as well as cabin flooring, providing considerable electrical and fire resistance, as well as sound dampening properties. Some aircraft also utilize these honeycomb structures in the construction of wings and other components, providing sufficient structural rigidity while also keeping the overall weight low, allowing for better fuel costs and cargo management. This concludes my presentation on Kevlar as a composite material.